Okay, any comments? So, okay, if not, I'll show just a little bit more calculation and I'll finish. Let's think about, okay, so this is the momentum. Now we can think about Newton's second. So first, let me remind you, P is equal to gamma. Let me remind you, this is the speed of the particle and mass of the particle. And actually, let's forget about vectors for the moment. We don't care. And here, this gamma u is 1 over 1 minus u squared over c squared. And now, in Newton's law, F is equal to, let me forget vectors, dp dt. Then I need to have d over dt, gamma u, mu. And I need to take derivative of this entire thing. Actually, let me write so that we see what we are taking the derivative of. So I'm going to take the derivative of this and then the derivative of that, and I'm going to simplify. So this is minus a half, 1 over 1 minus u squared over c squared cube, and minus 2u over c squared times mu plus 1 over 1 minus u squared over c squared m. Oh, this is m. I think I forgot. So this is minus a half cube minus 2u over c. This is du dt. Is that right? Yeah. And this one is du dt. Now simplify. So this, okay, let me just copy and simplify so that we can compare what we are doing. So this minus a half is gone with this. And I want to take, what do I want to do here? I see, I want to take it inside this. So this one I want to call this one and this one. I want to call this acceleration A. This is acceleration A. And I want to take it in the parentheses for M A. I have M A here. So this is, I feel like I can also take another factor, MA 1 minus u squared over c squared. So this is 1 over 1 minus u squared over c squared, and I have u squared over c squared, right? This one, and m is outside, so this is good. And here I have one more, so this is just plus 1, right? Is that true? Yes, that's plus 1. And now I have 1 minus u squared over c squared plus u squared over c squared. Cancel that with that. So this entire thing is going to be m a 1 over 1 minus u squared over c squared cube. Or let's write it a little bit like in my notes. So this is 3 over 2. And this was equal to what? This was equal to f. Now I want to write A in terms of f, A is 1 minus u squared over c squared, 3 over 2 f over m. Good, yeah, it seems to be correct. Good. Now, as you see, the key about this is as u goes to c, a, right? When u goes to c, you have 1 minus 1 is 0, and a, the acceleration is going to be 0, even if f is non-zero, right? Even if you keep pushing the particle, as you come closer and closer and to speed of light, you are going to have zero acceleration, right? That's why we say that for massive particles, they can never go at the speed of light, right? They can get faster and faster, but as you get closer, the acceleration is going to be zero. Good. Any questions? How much gas do we have in the tank? I can do one more small calculation, or I can finish it here. How many people want to stay for 15 more minutes? How many people want to go? Okay, let me do the halfway. Let me just do one more thing, and then maybe it's going to be like 5 minutes, and then we can go afterwards. Yes?
What about the mass in the second Newton's law?
Uh-huh.
Well, in the classical mechanics, we define it as some like inertia we get when we push the body. What about this mass? Is it same mass?
Yeah, it is the same mass. Like people, like I think you also asked the question. Suppose I am pushing the electron, and people in the early days, they define a relativistic mass. And I think even today some books have something about that. Today we don't do that. We say that the mass, for example, if you are pushing the electron here, this mass is rest mass of electron. There is no other mass. The only mass we have is the rest mass. And it doesn't change from, I mean, I don't know about the history. Maybe Einstein defined it and then he thought it was not good, so they just abandoned it. Okay. Good. So let me also define relativistic energy and finish it there. Maybe we can continue next time. So we have like velocities, we have momentum, we have Newton's law, and now is the time to think about relativistic energy. And for this, let me first start with kinetic energy. So kinetic energy is equal to, I'm going to use this work energy theorem. If you take a particle and push it for a distance of s, the change in kinetic energy is going to be f dot dx. That's the amount of work you do is the change in kinetic energy. And for this f, I'm going to use what we just wrote. So this is d dt gamma mu ds. And since we are physicists, we can just take from places and put them at other places. Doesn't matter. And so this one is ds over dt is going to be u. And I'm going to do by parts. By parts. So this is going to be u times gamma mu and boundaries from 0 to s minus gamma mu du. It's 0 to u, right? So you are starting from 0 speed and you are going to final speed. Let me put it like u prime, and it's going to u. Is that okay? And this one is also from 0 to u, and let's call this u prime. I think this one is fine. This is going to be gamma m u squared, and we have like a nasty integral, not nasty, but we need to take the integral here. So this is minus m 1 over 1 minus u squared over c squared u prime du, and I want to okay, how do I take this integral? I can define x is equal to 1 minus u prime squared over c squared. The x is going to be equal to minus 2u prime over c squared. Then let me just focus on that integral. So this is 1 over x, and this is u prime. So this is u prime. Whenever I see u prime du, I'm going to put minus c squared over 2 dx. Okay, now this integral can be taken. So this is minus a half c squared root x, right? And I need to delete this so that when I take the derivative, I have this one. Is that correct? Yes. And x was equal to 1 minus u prime squared over c squared, and the limits are from 0 to u. And if I put u, it is minus c 1 minus u squared over c squared. And if I put 0, it is going to be minus minus plus c squared. Okay, done. Now I can copy this entire copy. Okay. And this one is going to be the product here, like this. And what I have here is gamma m u squared plus mc 1 minus u squared over c squared plus mc squared. Let me check if I missed anything. So I think I seem to have missed something. Let me see. So I'm trying to take this integral. This is gamma mu, this one, and I took the integral. Oh, there's like an additional minus, right? This entire thing, and I think this one, right? This one is minus mc squared. Yes. So this minus mc squared. This minus this is plus. I think this is correct now, right? Is that? I think that's what I have in my notes, but sometimes my notes are also buggy. But anyways, so let me combine. Yeah, I think they seem to agree. Oh, I see. I think I also missed a factor of c here. Okay. So this is m u squared gamma plus this is m c squared. So this one seems to be c squared. Oh, this one is c squared, right? So this is c squared. Okay, this is c squared. This is c squared. I think everything makes sense. And now I will combine. So this one is 1 over 1 minus u squared over c squared. The first two terms I'm going to combine. So this is m u squared plus m c squared minus m c squared u squared over c squared, and divide this entire thing by 1 minus u squared over c squared. And so this one cancels this. Minus mu squared is going to cancel mu squared, and at the end I have minus mc squared. And it seems like what I have is gamma mc squared minus mc squared, but I want to write it like gamma minus 1 mc squared. Okay, so this is the kinetic energy, gamma minus 1 mc squared. Now I want to I want to define from the kinetic energy something called total energy, right? I can take this minus mc squared, like I can define something like this: kinetic energy plus mc squared is equal to gamma times mc squared. And when gamma is equal to when v is equal to 0, gamma is 1, kinetic energy is 0, and total energy is mc squared, and we are going to call this rest energy. Then this suggests defining E as gamma mc squared, the important formula, and when v is equal to 0, we have E is equal to mc squared. This is the famous equation we kind of like alluded in earlier class. Yes?
We say that the kinetic energy of the particle is relative, and also total energy also relative.
Yes.
Okay, then total energy of an isolated system is relative to the frame, or
Yes, yes.
but for an isolated system, the total energy of the system can be relative.
Mm-hmm.
But
Like total momentum is also relative, right? Momentum in one frame, even if there is no force, when you transform, it's going to change with respect to another frame.
then I don't understand the part. If we are looking something away from us, and it's an isolated system, that's called the bomb. So it's energy. If it is energy relative, then the effect of the bomb is changed.
Mhm.
How this can like?
Yeah, that's perfectly fine, right? Nobody says like energy has to be same in all frames. Energy itself is not an invariant quantity. That's perfectly fine. And momentum can also change, but I think I don't have time today, but maybe next time what we are going to see is energy will change, E will change, and P will change, exactly like CT changes and X changes, right? But we can combine these two things to see T squared minus X squared, and this doesn't change. This is like the same in all frames. And we are going to do exactly the same thing. We are going to combine something changing energy, another thing that's changing momentum, and if you combine them like this, what we call form momentum will not change. Okay? And energy can change, that's perfectly fine, from frame to frame. All right? Thank you.